Hello everyone, my name is Felicia and I have Joshua with me today. We are both from Empire Code Education, an education center which teaches computer science to children, teenagers and adults. Today, we are going to talk about making computer science education accessible for all. What are some challenges that educators face when teaching students with visual impairment? And what are some tools, strategies, and activities we can implement for an accessible, friendly class? We'll be taking questions at the end of this session. Before we begin, let's take a look at what is possible with the power of technology.
I'm Sachi Shaikh. I lost my sight when I was 7, and shortly after that I went to a school for the blind. And that's where I was introduced to talking computers, and that really opened up a whole new world of opportunities. I joined Microsoft 10 years ago as a software engineer. I love making things which improve people's lives. And one of the things I've always dreamt of since I was at university was this idea of something that could tell you at any moment what's going on around you.
I think it's a man jumping in the air doing a trick on a skateboard.
I teamed up with like-minded engineers to make an app which lets you know who and what is around you. It's based on top of the Microsoft Intelligence APIs, which makes it so much easier to make this kind of thing. The app runs on smartphones, but also on the Pivot Head smart glasses. When you're talking to a bigger group, sometimes you can talk and there's no response and you think, is everyone listening really well, or are they half asleep? And you never know.
I see two faces, 40-year-old man with a beard looking surprised, 20-year-old woman looking happy.
The app can describe the general age and gender of the people around me and what their emotions are, which is incredible. One of the things that's most useful about the app is the ability to read out text.
Hello, good afternoon. Here's your menu.
Great, thank you. I can use the app on my phone to take a picture of the menu, and it's going to guide me on how to take that correct photo.
Move camera to the bottom right and away from the document.
And then it'll recognize the text. Read me the headings.
I see appetizers, salads, paninis, pizzas, pastas.
Years ago, this was science fiction. I never thought it would be something that you could actually do. But artificial intelligence is improving at an ever faster rate, and I'm really excited to see where we can take this. As engineers, we're always standing on the shoulders of giants, building on top of what went before. And in this case, we've taken years of research from Microsoft Research to pull this off.
I think it's a young girl throwing an orange frisbee in the park.
For me, it's about taking that far-off dream and building it one step at a time. I think this is just the beginning.
Seeing AI is a free app developed by Microsoft that harnesses the power of artificial intelligence to help visually impaired persons navigate the world around them. The great thing about Seeing AI is that it does not just recognize one specific type of object. It can be used to recognize scenery, short lines of text, objects, currency, and the characteristics of friends around you. The result? A visually impaired person no longer needs to strictly rely on volunteers. And the fantastic thing about artificial intelligence is that it will improve over time. There are no limits to what people can achieve when technology reflects the diversity of everyone. 25 years ago, Seeing AI would have been merely science fiction. Imagine what the future could be. Let's start by understanding the challenges educators face when teaching digital literacy and computer science to students with disabilities. The two key challenges are a lack of specialized resources and limitations that current teaching methods have. Many with disabilities do not have access to learning computer science. In particular, students with learning or sensory disabilities like visual impairment are unable to find online tutorials catered to their specific needs or instructors who are trained to teach them. The second issue lies in teaching methods. For students with learning or sensory disabilities, Communication is an obvious barrier when teaching computer science. If a student has low to no vision, he would not be able to see a video tutorial or review codes that is being shown on the screen. Given that we do know a small handful of visually impaired individuals who are able to code and make a living from it, it is proved to us that these challenges can be overcome. All that is required is a structured curriculum to train educators and students globally. How do we make computer science accessible for visually impaired students? We'll be sharing a list of tools that will help them. To start, not everyone with an eye condition has the same level of visual impairment. Many partially sighted people can still see relatively well, and they may not need any of the items in the list. Hence, this list is just a guide. For people with low vision, their vision could range from being able to complete everyday tasks to being reliable on a caregiver. According to the World Health Organization, out of the 253 million people with visual impairment, over 85% have some form of vision left. For those with little or no perception of light, meaning that they are completely blind, they will need everything on this list to learn computer science. Let's go through this list now. Firstly, they will need a screen reader. This is a software that reads what is on a computer's screen using a synthesized voice. On Windows, a user will interact with a computer using commands on a keyboard, and the screen reader will read out what is on the screen. There are a few free screen reader options today, including a program called Narrator, which is built into every computer running Windows 10, as well as NVDA, an open source, third-party option. Narrator is a good tool for users who are recently being introduced to computers. Over time, students will discover one or more solutions that will work best for them when it comes to screen reader software. Next on the list is text-based programming languages. In our last webinar, we showed the simple, highly visual method of coding called block programming using the Microsoft MakeCode editor for the Microbit. However, block programming in general is not compatible with screen readers, and therefore is not suitable for visually impaired students. We will also need a code editor, which in simple terms is a special kind of text editor that is made for writing codes. Think of your popular text editor like Microsoft Word, but instead of typing notes or school reports, you write lines of code. If the student has low vision and will be using a screen magnifier, we recommend using the fantastic built-in code editor on the Microsoft MakeCode website. If the student has almost no vision and is using a screen reader like JAWS or NVDA, then we will recommend using Notepad++, a free and popular code editor. Notepad++ has a very clean, uncluttered interface. It doesn't take up much space on your computer, has several plugins for more advanced users, and is really simple to use. It has pretty much everything you need to get started. On screen readers, especially with JAWS, you'll be able to hear the line numbers being read out to you, which is incredibly useful when you're trying to find errors in your code. For this reason alone, Joshua uses Notepad++ on almost every coding project he starts with. For this demonstration covering MakeCode JavaScript on the Microbit, Joshua will be showcasing how he codes in Notepad++ and transplanting it into the MakeCode website for debugging once he's done. Lastly, we need a highly descriptive curriculum in a verbal and text-friendly format. This form of curriculum requires a lot of research and development, which we have completed. Specialized training for educators will also be ideal, as every student is different, and the trainer will have to cater to each student differently. Generally, if your student's vision impairment is at a stage where reading a screen for extended periods of time is a challenge, a screen reader will be beneficial. For today's webinar, we will share how we can teach the visually impaired computer science through the BBC Microbit. A Microbit is a pocket-sized computer that has 25 LED lights, 2 programmable buttons, a compass, accelerometer, light and motion sensors, and Bluetooth. It can be programmed to flash messages, create games, and more. Microbit is a great hands-on tool for teachers and students. We won't go into detail now, so if you haven't watched our previous webinar, We've included a link to it in the deck attached. Previously, we demonstrated block programming features on Microsoft MakeCode. Today, we'll demonstrate JavaScript on the same editor to enable the visually impaired to code on the Microbit. Students can jump straight into typing JavaScript code in Microsoft MakeCode. They can also copy and paste their codes from a separate editor, such as Notepad++. JavaScript is the most widely used programming language in the world. It is often used for web applications to animate websites, process logic for online games, and a lot more. The Microsoft MakeCode programming environment uses the static TypeScript, which is a superset of JavaScript. TypeScript is an open-source programming language developed and maintained by Microsoft. It is a strict syntactical superset of JavaScript and adds optional static typing to the language. TypeScript is designed for development of large applications and transcompiles to JavaScript. This means that anything you do in JavaScript, you can do in TypeScript, but not the other way around. MakeCode has an extensive reference section with documentation, which we have linked to in the deck. This is really useful for learning the functions and syntax of JavaScript for the Microbit. Alright, now that we know a bit about the Microbit, Microsoft MakeCode, and JavaScript, let's have a coding demonstration which will showcase some of the features in the MakeCode JavaScript editor. For this, we will have Joshua show us what coding with a screen reader looks like.
Hi, my name is Joshua, and I'm on a one-year-long internship program with Empire Code. I work closely with the management team on research and development for our computer science curriculum, which we roll out to our learning centers. Each piece of curriculum can take well over 100 hours to create, starting from research, followed by development, testing, and finally deployment. We are also really proud and excited to announce that we will be rolling out a curriculum which would make computer science learning accessible for the vision impaired like myself. And to get things started, I will demonstrate how a student with a vision impairment can interact with the Microbit.
Now this is going to be a close-up look at how I handle the Microbit, and I want you to pay special attention to how I use my fingers to touch the Microbit when I'm handling it. Also, hopefully this will be clear enough for everyone at home to see. So, first, let's start with how to hold the Microbit in the correct orientation. By feeling for the micro USB port at the top, this would allow us to find the top of the Microbit. Now in the front, we should have the two buttons A and B. A would be on the left and B would be on the right. We would also have our 25 LED panel screen at the front of the Microbit. Moving on to the back, we should be able to see the electronics of the Microbit. Well, you'll be able to see and I can't. But more importantly, we have our reset button over here. Over here, which would be handy in letting us reset everything back to square one when we need it. Also up here, at the right side, we have the port for the battery pack, which would be an optional accessory which we can attach to the Microbit, and we will not be using this today. At the bottom over here, we can find the pins which would allow us to attach optional accessories to the Microbit, and again, we will not be using this today. So if you watched Felicia's first webinar on introducing the Microbit, none of this would be new to you, but this is just going to show you how a person like myself would be able to feel the Microbit in order to understand what I'm doing when I'm handling it. Now, one thing you might have thought about and realized is if a person cannot see what's being displayed on the LED screen, how would they be expected to know exactly what's being shown? And the short answer is, for people like me who can't see, we wouldn't be able to know directly what is being displayed. But with a little bit of visualization, we would be able to understand and visualize what kind of effect we are having on the Microbit when we start coding.
So to get things started, let's head on over to my computer and I will show you what a screen reader looks like. First, let's start things off by launching NVDA. So what I did was I pressed the keyboard shortcut to launch NVDA, which on my computer is Alt-Control-L.
And what NVDA is, just to introduce all of you to this piece of software, NVDA is a free and open source screen reader which allows people with vision impairment like myself to be able to interact with the computer. NVDA would read what's on my computer screen, and if I were to toggle to my web browser, you'll be able to see that it's starting to read stuff. Now normally my screen reader is set to a much higher speed, but for today we'll slow it down so that you can actually understand what the screen reader is doing for me. First, let's begin by going to the MakeCode website. Go to the address bar. Now, the MakeCode website can be accessed by going to makecode.microbit.org. And it should be loading. Alright, cool. And what we can do is create a new project. Should be creating a new project. There we go. And if I were to go to the top, we have this thing called Skip to JavaScript Editor. So if I were to select that, it should bring me to the text box and I can start typing. So let's delete this default piece of code and I can just type some random words. Okay, this is not actual code, but this is just demonstrating to you how someone like me can type in this text box. And the nice thing about the Microsoft MakeCode website for the Microbit is that it's completely accessible for people with screen readers like myself. So what we'll be coding today on the Microbit is a game inspired by an eyesight test which is administered by this machine called the Humphrey Visual Field Analyzer. So what this machine is and how this eyesight test works is a patient sits in a chair, they're given a clicker to hold, and they rest their chin on a chin rest while staring into this dome-shaped structure, which is part of the Humphrey Visual Field Analyzer machine. Now, when the eyesight test begins, what happens is a series of strobe lights will be flashed on the dome-shaped structure, which is part of the machine, and every time the patient sees one of these strobe lights, they will have to press the clicker that they were handed before. So based on the patient's reaction times, the machine would run an algorithm to determine how much vision field the patient still has remaining. Now, the Humphrey Visual Field Analyzer is used to diagnose a number of eye conditions, including glaucoma, which is the eye condition which I happen to have. The machine can also be used to determine if a patient with a minor eye condition is still eligible to drive. The target age group for this project will be 12 years old and above, and the tools that we will need for this project would include a microbit, a computer, a USB cable, the NVDA program, and Notepad++. Concepts we will cover in this project would include inputs, variables, if-else conditions, sequencing, and functions. In total, the project should take about 50 minutes. So now that we understand what we'll be coding today, let's get started. Now to recap, we can break down our game into 3 key components. Number 1, the logic behind the game itself. Number 2, what happens when the player gets things right. And number 3, what happens when the player gets things wrong. Now remember that the player is supposed to press the A and B buttons when they see an LED flash on the screen. So if they get it correct, what they'll see is a tick that would appear on the screen and 1 would be added to their score. And if the player hits the A and B buttons when there's nothing on the screen, it means that they've gotten things wrong, and the microbit will flash a cross sign on the screen with 1 point being deducted from the player's score. Now this would continue to repeat over and over again until the player hits the B button to stop the game. In order to get started with this section of the code, we will need to introduce an important concept called functions. Now, a function is basically a piece of code that you can reuse over and over again, and to illustrate this, we'll use a real-life example. Let's imagine this. Let's say I'm an owner of a famous Italian restaurant that serves a secret recipe of lasagna. Now, every time a customer walks into my restaurant and orders a lasagna, they would expect the food to be exactly the same. If it's any different or any worse, they would not want to come back. So every time the customer makes an order, which you can think of as an input,
the order would go to the chef, which you can think of as our computer, and he will process our secret recipe to serve up the lasagna, which would be our output. So this process of creating the lasagna can be repeated over and over again, and more importantly, our output, the lasagna, would be the same every single time. This is a good example of how functions work. So functions allow us to avoid having to rewrite code over and over again. We just write it one time and we can call on it to use repeatedly. This is especially useful if our piece of code is really long, and also by separating the code by writing it one time and calling it under a function, we can also just debug that piece of code once instead of having to find every instance of that code appearing just to debug it. This means we can debug or fix faulty pieces of code more efficiently, and when it comes to coding, being efficient is extremely important. So we can start coding now. Now, to make the process a little bit easier for me, I'm going to use this program called Notepad++, which is a simple text editor for coding, which is really easy for me to use and really friendly when it comes to coding on with a screen reader. So let me just create a new file that I can save. Microbit project. Let me save it under my desktop, and that way I have this text file from which I can copy my code and paste it into MakeCode once we're done. So let's begin. We talked about functions, and let's create our function for the situation when our player gets things correct. So let's call it I'm just going to be typing this and I'm going to explain it in just a bit. As you can see over here, I've typed two sections of code, one called function player correct, which we will be using for the scenario when our player gets things correct, and one called function player wrong, which I guess you can sort of get the idea by now. Now, when we create functions in JavaScript, we use the function keyword to indicate that this section of code would be a function. And within the curly brackets that you see, called braces, this is the area where we write our code in. So let's get started. Going to do some indentation. Within a function, it's always a good idea to use indentation, and I'm going to type a piece of code here and I'm going to explain it in a bit. So as we went over earlier, within the scenario where the player gets things correct, we want to show them a tick. And in MakeCode, there's actually a built-in function called basic.showLEDs, which is what I just typed right here. And what we can do with this function is we can activate any one of the LEDs on the Microbit's screen by using full stops to indicate an LED that is turned off, or a hex sign to indicate an LED that is turned on. And I'll just show you in a bit how this is going to work. First, we want to imagine if we were to replicate the Microbit's 5x5 LED screen, how would we represent each individual LED on the screen, remembering that a full stop represents an LED that is turned off, a hash sign that represents an LED that is turned on, and what we want to display on the screen would be a tick. So doing a little bit of visualization, what we can do is 1, 2, 3, 4, 5. 5 dots on the first row. 1, 2, 3, 4. 4 dots and 1 hash on the second row. 1, 2, 3 dots, 1 hash, and 1 dot on the third row. And for the fourth row we have, let me get things correct, 1 hash, 1 dot, 1 hash, and 2 dots. Oops. Yep. I don't want to use a comma, I want to use a full stop. And finally, on the last row we have 1 dot, 1 hash, and 3 dots. And here we go. As you can see, we have a rough representation of a tick. That's how we can plot the LEDs on the Microbit screen. Now we need to do the same thing for the scenario of player wrong. And let me just get rid of this extra tab, and we can create a cross under player wrong. 3, 4. Okay, again, we'll use the function basic dot show LEDs. Okay. There's something that I'm doing here, which is remembering to close my brackets all the time. In coding, you use a lot of functions with open and close brackets, and you always want to remember that whenever you open a bracket, you definitely want to close it. Okay, so for the cross, I think this is a bit more straightforward. We have 1 hex, and and for the last row, oops. There we go. So under function player correct, we have a lovely tick, and under the function player wrong, we have a big cross, which the player would see when they get things wrong. And there we go, we have created 2 functions. We have already taken one big step towards completing our coding project. So next, let's have a little bit of a think on how the player is going to interact with the microbit while they are playing the game. Remember that the player has one key form of input when they are playing the game on the microbit, which would be through the buttons. Just to recap, button A would start the game, and during the game the player hits buttons A and B together whenever they see an LED flash on the screen. Finally, to stop the game, the player would hit button B, and this would trigger an event that would show the player's score. What we need to do next is to code what happens when the player presses button A. So let's create a new line, and to do this we'll be using a new function called input.onButtonPressed. And what this would do is it will recognize what button is being pressed on the microbit. Now input.onButtonPressed is a function that is built directly into MakeCode. For it to recognize which button we'll be using, we need to specify, in this case, button A, with a comma, the word function, closing our brackets, and there we go. Now you might be wondering why we're typing our code in this particular way, with the word button A with a capital B and the capital A with a comma and the word function following that. This is just a syntax of MakeCode JavaScript that is used for the microbit. Syntax meaning the language that is being used. In this case, we are using TypeScript, which is a modified version of JavaScript created by Microsoft and adapted to be used in the case of the microbit. So naturally, each language has rules like grammar and sentence structure, and in this case, when we declare our buttons, for example, the input.onButtonPressed, we need to use capital letters for our B and A for button.A. We need to write the word function, and we need to use this specific brackets. So just to give you a bit of context on what we're doing. Now within these brackets, we'll be typing the code that we want to execute when the player presses button A. In this case, we want the game to start. So what we need is something to keep track of when the game is being played and when it is not being played. And to achieve this, we'll be using something new called a variable. Now let me just type my variable here first, and then we can go into explaining it. So let me use my 1, 2, 3, 4 for indentation. Okay, play game. Play game equals true. Now this would be my variable. So to explain variables simply, just think of a variable as a container for a specific value. For example, if I were to just create a blank page here, just for illustration purposes, if I were to say that x is a variable with the value 5, it just means that x equals to 5. Yep, 5. There we go. So you can think of x as being the container for the value 5, or you can think of it as algebra as well. But just keep in mind, not all your variables need to be x. You can give your variables names like my name. For example, you can have text or strings be your values in a variable, and variables can also be Boolean. What is a Boolean value? A Boolean is simply a type of data that can either be true or false. So one thing you might have thought about is we have this play game equals a true, but we have never declared or stated that this variable exists. We do have to declare it, and to do this we'll go to the top of our code and we'll use this keyword called let play game equals to false. Now what we have done here is we have created the value play game and we have assigned it the value false by using the equal sign. So what we did here up here on line 1 is we have allowed the computer to register that there will be a variable named play game so that we can refer to it in our code, like when we change the value from false to true when we have the player press the button A. So one thing you might have realized is that for our section on input.onButtonPress button A, we are more or less done, because the only function of button A is to trigger the activation of the game. And since we're using the variable play game to keep track of whether the game is on or off, and we've already typed play game equals to true, it means that our button A has done its job, meaning that when our player presses button A, play game would turn into true, and then that should trigger the start of our game once we type more code following this section. So that's good. Let's continue on to our next section. After the player presses the button A, what happens is the game would activate. But one thing, before we go on to program the game itself, we need to have to think about the game logic. So essentially the game has two functions. Number one, it needs to be able to check when play game equals to true. Only when play game is true, then the logic of the game will start running. Number two is the game needs to have the feature to blink the LED lights, and we wanted to do it randomly, because if the blinking of the LEDs on the Microbit screen becomes predictable, then the purpose of the game is essentially defeated. So with this in mind, let's start coding our game logic itself. Now remember that we want our game logic to continuously run in the background, and to achieve this, we'll be using what is called a forever loop. So let me just type it and then I'll explain. So this is what a forever loop looks like. And basically what a forever loop is it's a section of code that would run over and over and over again in the background as long as the microbit is on. So you'll always check whether or not the game is on by referring to the play game variable. So what we do is we'll check it using a conditional statement in a while loop. And let me just type it before I explain what a while loop is. 1, 2, 3, 4. Okay, so this is what a while loop looks like. While play game equals to true. And there we go. A while loop is a section of code that will continually run as long as a given condition equals to true. So to illustrate this, let us use the example of a classroom of children waiting for the school bell to ring. The condition we will be using in this case would be school bell has not rung. So as long as school bell has not rung equals to true, Your children would stay in class and continue having lessons. But once school bell has not rung equals to false, you would exit the loop and the code will move on to something like, for example, children will go out of class to play. Now that we all know what a while loop is, let's move on to code our game logic. Now every single time that our code iterates through or loops through the while loop, I want the microbit to clear the screen. And we do this by using a function called basic.clearScreen. So let me just type that in. 1, 2, 3, 4. Okay. So basic.clearScreen does exactly what it sounds like, which is to clear the screen, and so that every time the game goes one round, we start the game on a fresh screen. Next, we want to consider that our game can only be in two states: when there is a random LED being generated on the screen, and when there's nothing being displayed on the microbit's LED screen. Now to do this, we are going to use another variable called chanceGenerate. And chanceGenerate will be keeping track of whether or not the LEDs will be generated. And what we want the states of the game to be in, we want it to be random. So whether or not an LED appears or does not appear on the screen, we want this to be completely random so that the game does not become predictable. And to use this randomization, we'll be using the random module in JavaScript. To access it, what we do is we type math, and in this case we'll want it to generate a random number for reasons that we'll explain later. So in order for it to generate this random number, we'll be using random range, and the numbers I'll key in will be 0 and 1. I'll explain why in just a second. chanceGenerate is a variable, like I said, so we need to declare it at the top, like our let play game equals to false. And in this case we type let. Oops. We type let chanceGenerate equals to 0. So it's holding a value, a numerical value, until it reaches this section of the code where its value is either determined to be a 0 or 1. Let me explain what is happening here, and there is a good reason why I am using math.randomRange. What is happening here is that chanceGenerate can either be a 0 or 1, and this would happen randomly. Now what we're going to do is assign 0 and 1 its own meaning. If chanceGenerate equals to 0, I want the microbit's LED screen to display nothing. But if chanceGenerate equals to 1, I want the microbit to generate a random LED to flash on the screen. Since chanceGenerate has randomized values, it can be 0 or 1, but whether it is 0 or 1 is completely random. By giving it this function, what we are doing is we are giving meaning to the numbers 0 and 1 so that we can have the game logic determine whether or not an LED would flash on the screen or not. And we are ensuring that when this happens would be completely random. And so to determine what happens when chanceGenerate equals to 0 and when chanceGenerate equals to 1, we'll be using conditional statements in the form of if-else statements. An if-else statement is a type of code in which you can execute a certain series of events based on a specific condition or specific set of conditions. So to use a real-life example, I can tell you, if it is raining, bring an umbrella, else leave the umbrella at home. The key difference between an if statement and a while loop is that the if statement will only execute your code once when your condition is true, whereas a while loop will continually repeat your code as long as your condition is true. Now that we understand what if-else statements are, let's create our very first if statement to check if chanceGenerate is equals to 0. If so I've just typed if chanceGenerate equals to 0, then we want the LEDs to be off, remember. To do this, we'll be using a variable to keep track of when our LEDs will be on and off, and we'll call it, in my case, I'll just call it blink equals to false. Blink equals to false to indicate that no LED would show on the screen. And yes, blink is a new variable, so let's declare it at the top once again. Let so this new Boolean value for the variable blink. Let's go back down, and we just gave it the value false so that it has something to hold until we reach this section of the code at the bottom here. When blink can be equals to false, or later on when we'll be typing the code for when blink equals to true. Next, we want our code to pause for a random amount of time to make sure that the microbit takes a break so that it doesn't continue just running. If not, what happens if you don't put pauses in your code, especially when it comes to games, is that your game would just run at an incredibly fast speed, and that's not something that your player would be able to keep up with. So we want to create a pause, and we want it to be random as well, so that our player can't just wait for a certain amount of time before they can expect an LED to appear. So to generate a random amount of time to pause, we'll be using basic. Basic.pause is a function that is built into Microsoft MakeCode JavaScript. So basic.pause, and to give it a random amount of time, we'll use math.randomRange yet again. And this time we'll give it the range of 800 to 1000. In the case of our pauses, it measures the amount of time in milliseconds. So in this case, it'll be pausing for a random amount of time that is anywhere between 800 to 1000 milliseconds. Now that completes our logic for the case where chance generate equals to 0, meaning that there will be no LEDs displayed on the screen. Now let's move on to what happens when chance generate equals to 1, meaning that we want an LED to be generated on the screen. Let's go to the end of our first if statement. And if you think about the logical progression of our if-else statement, you can think of it this way. Since chance generate only has two possible values, it can only be either a 0 or a 1. If it is not a 0, it is definitely a 1. So we don't actually have to write a new if statement. We can just continue typing by saying else, meaning if chance generate equals 0 dot 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 else, and then that would be when chance generate equals to 1. So first things first, when chance generate equals to 1, blink will be equals to true, as opposed to before when chance generate equals to 0 and blink equals to false. And next, we will take a look at how we can plot the LEDs on the Microbit's screen. Remember that we want to plot the LED randomly, that's one thing, and keeping in mind that one LED would be appearing at any given point in time, so there wouldn't be more than one LED being generated. One thing we should do is type led.tlt. So we'll be using this function called led.plot to activate any one of the 25 LEDs on the Microbit screen. So led.plot, as it might suggest, would be a function that allows you to plot any given LED to appear or light up on the Microbit's screen by indicating an X and Y value. Now one thing you might be thinking is why we'll be using led.plot instead of something like show LEDs, which we're using at the top. Yeah, instead of using something like basic.show LEDs, and this would be a very good question. And the answer to that is, when we are using basic.show LEDs, we are sketching an image on the Microbit's LED screen. So for example, in this case over here in player function player correct, we are sketching a tick sign to appear on the Microbit's screen, and in function player wrong, we are sketching a cross sign to appear on the LED screen. In comparison, when we want to, in the case where transgenerate equals to 1, we want to randomly generate one LED to appear only. It's much more efficient of our code space to just type led.plot and indicate an x and y value. Well, like I've said many times, the LED that would appear on the screen during the game would be at a random position at any one of the 25 LED points. So to make this random, we'll have to have a random x value and a random y value. So to achieve this, we'll be using our good friend math.randomRange yet again. And we'll give it a random value for x and for y. There we go. Now for any one of the LEDs on the Microbit's 25 LED screen, remember it's a 5x5 grid. For each of them, their x values can be anywhere from 0 to 4, and their y values can similarly be anywhere between 0 to 4. Now for our purposes, we don't really have to remember which LED corresponds to which coordinate because we're just making it random. So let's just type math.randomRange0 to 4 for our x value, and for our y value, let's do the same thing as well. 0, 4. And that should generate a random LED to appear on the Microbit's screen based on x and y coordinates. Okay, cool. Next, let's do my indentation yet again. And let's have the program pause for 1 second or 1000 milliseconds. Basic.pause 1000. So basic.pause, like we mentioned previously, is a function in MakeCode that allows us to pause the program for a specified amount of time in milliseconds. And in this case, we are placing 1000 milliseconds, which equals to 1 second. And okay, oh yeah, one thing before we move on, to explain why we have basic.pause 1000 over here. Remember that we mentioned in our games, if we don't include pauses for the game, the microbit would just run the entire process incredibly quickly. So by placing basic.pause 1000 immediately after the LED flashes on the screen, this gives our player enough time to react to when the LED is flashed. Now moving on, remember that in our game, when the game is running, the player presses A and B at the same time to use it as the clicker, so that if they see the LED on the screen when they press AB, this shows that they have registered a hit. So just to recap the rules of the game, when the player presses AB when there's an LED to flash, we will launch function player correct and display a tick for them and add 1 to their score. If the player misses by pressing AB when there's nothing on the screen, it would see the cross that we will call from function player wrong, and 1 point would be deducted from their score. So with that in mind, let's begin. And we'll have our code for input.on button pressed button AB. Using the correct syntax once again. And this would be the code for the section of what happens when our player reacts to the game that they're playing. If we have a think about the logic in this section when the player presses AB, there's two possible scenarios that can occur: when the player is correct and when the player is wrong. Sounds pretty obvious, but by identifying this, we can think about what we need to do. So first, before we get into that logical sequencing, let's make it so that every time they press the button AB, it clears the screen. That way we can ensure that there will be absolutely no overlap in terms of our LED generation. So let's do that. Basic dot clear screen. Okay. And to check if there is actually a LED being flashed on the screen, we'll be using something that we declared earlier that didn't have a very clear purpose, which would be our variable blink. So remember that in our game logic, we said that blink equals to false when chance generate equals to 0, meaning that we did not want any LED to be flashed. And when chance generate equals to 1, we made blink equals to true, and we had the LED randomly generate, meaning that there would be an LED generated on the screen. So we can easily make sure that we know which is which by using conditional statements yet again in the form of our if-else statements by checking if blink equals, oops, sorry. So we can check if there is an LED on the screen by checking if blink equals to true. So if blink equals to true, it means that if the player presses AB and blink equals to true, this means they have scored a hit. So we would like to reward them by showing them a tick and adding 1 to their score. But before we do that, we will want to revert blink back to equals to false, so that we do not have any false positives. Let's say if they hit AB twice while the LED is still on the screen. So blink will be equals to false, and we would like to call on function player correct by just typing So when I type player correct with the parentheses, this actually what it does is it calls our function player correct, meaning that it would request for player correct to run the code in it, which would generating the tick sign using basic.show LEDs, as we can see from the lines all the way up here. Yep, over here. So player correct will initiate when the player is correct. And one more thing, we need to add 1 to the score. So we would have a new variable called score, and we would add 1 to it by using this operator called plus equals to 1. So plus equals, it allows us to add things to a variable that contains a numerical value, in this case score, and we do need to declare a score, so let's go back up to the top. And in this case we'll let it start with 0, because every good game needs to have a score starting from 0. Wouldn't make sense to give our player a score of 10 before the start of the game. And every time the player gets it correct, 1 would be added to their score. Now let me just check my code to make sure everything is in order. Yep, okay. Next, we need to code for what happens when player is wrong, meaning they are hitting AB when there's nothing on the screen. And keeping in mind that if we recall from chance generate only had 2 possible values, which was 0 or 1. So after we said if chance generate equals to 0, we did not have to declare a new if statement, we just went else. Similarly, with blink, it can only have 2 possible values being a Boolean value, so it can only be true or false. Keeping this in mind, if you look at the logical sequence of our code, we do not need to have a new if statement. We can just say else, and this would indicate the situation when blink equals to false. Now, when the player is wrong, we need to punish them by showing them the cross sign, which we would call from player wrong, function player wrong, and again, we would call the function by typing the function's name with the parentheses, and we will deduct 1 from their score by using the operator dash equals. So minus equals 1, score minus equals 1. Now another thing that some coders like to do is they'll type score plus equals minus 1. Now I can't speak for everyone who does this, but I suspect it has something got to do with the fact that when the dash sign is next to the equal sign, it can be hard to see which is which, some people prefer to use the plus equal sign to indicate that the value for a numerical variable, in this case score, is having its value changed. Now, I personally find this quite long-winded, and if the problem with certain coders is visual, obviously I wouldn't have the same problem, so I'll just use dash equals. In JavaScript, you can use either one. It's entirely up to you. So that's that in terms of changing the value of score, in this case to deduct it by 1 point. Another thing you would have noticed is that we did not declare blink equals to false, and we didn't do this because blink in this case is already false. So there is no need to declare blink equals to false to ensure that no false positives occur. Finally, at the end of this block of code, we want to put a pause and a clear screen again to make sure that the player has enough time to react to things and to ensure that the screen is completely blank before the cycle continues once again. So let's do that. And basic.clear screen. There we go, we are almost done. Now the final section of our code would occur when the player presses the button B to end the game. So yet again, we'll be using input.onButtonPressed. Button B. So input.onButtonPressed button B. And remember that button B is used to end the game. To end the game, we'll need to declare play game equals to false. And blink would also be equals to false. And finally, when the player presses B to end the game, we want to give them a sort of parting gift in the form of showing them their score. So to do this, we'll be using two functions, one called showString and the other called showNumber. So let's type that in. So we'll use basic.showString. Basic.showString allows us to show text on the screen, strings being text in programming languages. So in this case, we want to show them the word score, and we want to pause for 100 milliseconds. And finally, we want to show them a number, which would be their score. So we use basic.showNumber, and we'll just use the variable score, which is a number after all. So we should be done. One last step would be to copy our entire code here. And I'll paste it into the JavaScript editor on our Microsoft MakeCode website. Okay, so it's telling me that we've made 5 formatting errors from line 25 to 55, so let's check it out. Give me a while to find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. The one disadvantage about using NVDA with Notepad++ is that JAWS, which is another screen reader, would read me the line numbers, so I don't have to count manually. Let me see what's the error here.
Okay, I think I'm supposed to add a space here. Oh, so that means I've made a mistake in all my other input dot on button presses. Let me just change that as well. For our AB. Okay, so you might realize that some programming languages, and I guess TypeScript is one of them, would be both case sensitive and space sensitive. So in this case, I think it's making a fuss about whether or not I have the space behind the word function. So let me save that and copy over. Two formatting error edits on line 29. Let me check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, it's my while loop. So let me check that. Okay, I have a space here. Okay, I don't have a space here. So I should have everything in order now, and it shouldn't be telling me if that there's any more errors. There we go. And that's it. So the nice thing about the MakeCode website is that it will throw me an error like it did just now, earlier, to show me where I'm making errors and on what line it can be located on. So by doing this, I will be able to go into my editor like Notepad++ and find the errors based on the line numbers that MakeCode has been giving to me. Now you might realize by now that coding can be quite a time-consuming and arduous process, and you might not follow everything that has been happening in this webinar. But don't worry, because this project that we've covered is considered a relatively advanced project. So for someone like me, it can take many months and possibly even longer to get good at computer programming. But that's the thing about computer science, is that it takes practice to make perfect. For me, I've been coding for slightly over a year, so you can say that I have some degree of experience here, and that's why I'm more comfortable in typing and troubleshooting in that sense. But for all you educators out there, don't fret and don't worry too much, because with enough perseverance, someone like me will be able to code and to catch up with everyone else on the same playing field, and that's what we're trying to demonstrate today by doing this coding demonstration. So thank you all so much for watching. This was Joshua with Empire Code, and we'll be moving on back to Felicia to wrap up this webinar. Thanks for watching.
Empire Code is an authorized reseller of the Microbit. Do drop us an email at sg@empirecode.co or visit this link on the website www.empirecode.co. To follow on from this webinar, we have an 8-part series of this JavaScript course and another 8-part series of Python programming made accessible. Visit our site at empirecode.co/education/online for more information. Please visit microsoft.com/enable to discover modern approaches for digital inclusion, as well as tools, products, and services designed for all abilities. You also have access to the Ability Hacks book, which will give you a behind-the-scenes look into developing technology for people with disabilities. Thank you for attending our webinar, and we hope that you're ready to help us make computer science accessible. Please feel free to email me with any questions that you have throughout your Microbit journey.